Can you hear me now, Kaylee?
Yes.
Good, thank you. Sorry about that. So this particle has a wave function. That's a wave, right? It's a complex wave. It's a wave of two components. And we showed that it normalizes the 1 over the square root of pi, because the area that this wave function subtends in complex space is a circle, so it gets surface area pi. Normalization constant is square root pi e to the ikx. Right? So it's got this wave-like behavior. It can also be minus ikx. That's just a wave propagating in the backwards direction instead of the forwards direction. So we assign space. This is 0 at the door, and this is going to infinity as we go towards Kaplan, the Boston Post. E to the ikx is a particle that starts at 0 and moves this way in time, has momentum in this positive direction. And then negative ikx is one in the opposite direction, towards 0. Okay, so it doesn't really matter which one we pick. Again, this is an infinite space. Going left is no different than going right. So it doesn't really matter what one we choose. So we can always write something like this if we wanted. That's perfectly fine. I'm just going to kind of just put this off to the side because it's not super important. Right? But it's good to know that, again, it's a wave. A wave can move in both directions. So we should consider both. Maybe one's more relevant to us than the other, which is how we choose our experiment. The result of this, as we saw, was that this has a continuous energy spectrum, which means that the particle can be at any energy it wants. So it has a continuous momentum in energy space or spectrum. All right, and the reason why that is we saw that the energy, kinetic energy of this system, E sub k, is this h bar squared k squared over 2m. Did I introduce the h bar constant last class, right?
You introduced it, but you didn't define
I didn't give you the value for it yet. Oh, great. Today is a good value time to talk about it. All right, great. So I'm sorry I haven't done this yet. Today's a good day to talk about this number because we see it now. And of course, this is related to the fact that the momentum, remember that just remind yourself that the energy, the kinetic energy, T, is p squared over 2m, which means that the momentum, the absolute value of the momentum, is h bar k, right? Where k is some number. So k is a real number. Okay, and h bar is a constant. Right, and it's the absolute value of the momentum is h bar k, because again, it could go this way or this way. Right? We don't really know. Doesn't matter. The direction doesn't matter. It can propagate either way. And so the absolute value of the momentum is h bar k. We don't know anything about the direction. But we know it's moving with this momentum. Now you may think, what the hell is the momentum of a wave? I think that's an important question. It's just some sort of energy. Right? That the wave, this wave is carrying some energy. So when it collides with something, it's going to impart that energy on it, and that's transferred via momentum. And we talked about how it hits the foil, right? The foil starts moving when the photon hits it, right? So it's just some sort of energy content that's stored in a wave that's transferred into a physical object that is then converted into, say, physical, mechanical motion of an object. And we're not going to focus too much on the math of this, but that's kind of what it means. So if your momentum has a positive value, this corresponds to motion of your particle in space. The particle is moving along the next direction. If it has a positive or has a non-zero momentum. All right, we don't have to worry about that too much. It's not a big deal. We're not doing physics here. We're doing chemistry. All right, so let's stop and look at this h bar number. We're going to be everyday class. So I'm sorry I haven't introduced it. Yeah, so we have this constant h bar. And as we can see, it's related to momentum in some way, right? K is just a number. It doesn't have any units at all, as far as we know. It's just a number, just some index for how much momentum you have. We have 1 unit of momentum or 2 units of momentum. And what are the units of momentum? What are the units of h bar? And so K is 2. This means the momentum is 2 h bar, whatever h bar is. So H bar has units of momentum. Or proportional to a momentum at least. It has some relationship to momentum. Right, and so H bar is called Planck's, and I'm going to put it in quotations. I'll define what I mean by this in a second. This is called Planck's reduced constant. Sorry, everybody on Zoom. My Zoom crashed. Originally measured by Planck 19th century to an accuracy of 10%. I shouldn't say precision and accuracy. His precision was a little higher than that, or a little lower than that, but it's accuracy of 10%. Right? And when you see this number, it's really, really impressive how we can measure this to 10%. So the value of H bar, and let me get the exact value. It's defined exactly now. It's not a number that has an uncertainty in today's world. It's defined exactly. H bar is 1.05457. 1817. I've given all the digits. We won't use all of them, but these are the digits. This is the full number times 10 to the minus 34 joule times seconds. That's a tiny number. Right, we should think about these units a little bit. Joule seconds is kind of a strange unit, right? But when we think about our system being a weight, carrying some energy with it, we'll realize that this makes a lot of sense. All right, first of all, it's a really small number. Really, really small. All right, what this means is that what we're going to find is that the seconds has something to do with inverse frequency. Or frequency, let's just write this down. Let's think about this number for a second. All right, let's do a little dimensional analysis. All right, so I'm just going to write it on the side. We're just going to round it down just a bit. 0.0545 times 10 to the minus 34 joule seconds. Oh, we got this number. Let's get a sense of what this number means. All right, so let's think about the units. A better way to write these units, in my opinion, is instead write it as joules per, this is kind of weird, hertz minus 1 per hertz, where hertz is cycles of 2 pi. Sorry. Let me start over a second. Let me cancel this. Let me erase this. I apologize. Let me introduce a different version of this number. Right? And we're going to compare the two. We're going to see two different versions of H. They're exactly the same, but they have a slightly different interpretation. So let me just write that down. And then I think it's easier to see the math. All right, so this is what's called the reduced constant. Or we often call this, whenever you hear me say H bar, that's what I mean, right? It's an H with a little bar through it, right? We call this the H bar. There is a regular H as well, And depending on what context we're in, we'll use either one. We can also interconvert them. There's another one called H, which is 2 pi times H bar. Right, and this H here, this is what we call Planck's constant. All right, so Planck's got 2 constants named after each other that are related by a factor of 2 pi. All right, so the value of this is just 1.05 times 2 pi, which is like 6 something. So this number is on the order of, write it down. 6 point, yeah, I know this by heart. 6.634. Forget the next digit off the top of my head. Oh, I'm sorry. I think I'm confusing it with the mantissa of Avogadro's number. 6.626 times 10 to the minus 34. Okay, so there's 2 different forms of this constant that are different by 2 pi. All right, so let's think about why there's a 2 pi factor between the two. Why do we even care about this number times 2 pi? And the secret is in the units. So the units are like this. So H bar, right? If you think about it, think about, again, remember, we're always moving in a circle in the complex space. We have a wave that's moving in complex space, right? So it's the phase of this wave, right, as it moves through all the possible positions of its orientation, goes through 2 pi radians. There's 2 pi radians in the entire circle. Right, so this H bar, if you will, or this H, if you will, has something to do with those 2 pi radians. And it's H bar times 2 pi, right? So what that means is that H bar has something to do with the energy content and during a frequency that's the frequency of the system moving through exactly 1 radian of its phase versus 2 pi. Right, so if you have a wave that goes through an entire period and it goes up, down, and it goes back to its original position. When we want to think about the momentum or the energy of that wave from the perspective of a frequency that is how you know frequency of a wave, which is 2 pi radians, a whole period, how many periods per second, we use H. But if we're talking about something in a per radian sense, right, like an instantaneous frequency, some speed that's in units of per radian, then we use H bar. Right, so H bar has to do with, so the way I like to think of it is it's the joules contained in a wave with angular frequency of units radians per second. Right, remember radian's about 60 degrees. It's just kind of a fundamental unit of angle that we use in math. All right, so the way that I like to think about this, radians aren't a real unit, so they're hidden in here. There's really seconds in here. So there's actually radians in here hidden, but we just don't see it because it's not a real unit, so we don't represent it. So what the kind of like brute force units of H bar are, so the units of H bar are joules per, and I like to write it like this. Sorry, let me do it like this. Joules divided by radians per second. Right, and if we just ignore the radians, this is joules per second. Okay, so what this means is that if we have a particle that has a frequency, angular frequency, or some momentum of some number, then H bar tells me how many joules are stored in that wave. Right? H, on the other hand, is the amount of energy stored of a wave with total frequency, which is cycles per second, how many periods, 2 pi radians per second are evolved. In units of hertz instead. So this is joules contained in a wave with radial frequency of units cycles per second, which we could also just call periods per second. Right? And how many periods of a circle does the wave go through? Right, 360 degrees. How many periods per second? And the unit we use, that has a real unit in chemistry or in physics or in real life, and that's called the hertz, HC, hertz. Right, when you tune your radio, it's in megahertz, right? If you're doing FM, right? And that tells you the carrier frequency of that audio, carrier frequency of the radio signal is cycling as it's going through that many periods per second. So 100 megahertz radio signal means that signal is oscillating at 100 million periods per second. That's what 100 megahertz is. Right, so the units of H are joules per hertz, which is the same as joule seconds. Right, so they're just slightly different, right? They're just different by 2 pi. One's in radians and one's in hertz. And so when we talk about light, for instance, when we talk about light in the frequency of light, we often use H. Because when we talk about light, we represent it in terms of its radial frequency, which is its cycles per second, which is in hertz, right? 100 periods per second. That's a 100 hertz signal. Right? So for H, we often use this for light. So used for light. Light frequencies. And H bar is more useful for momentum. Because what we're going to learn angular momentum eventually, because we're going to have an electron orbiting a proton in a hydrogen atom, we're going to have to think about its momentum in an angular sense because it's orbiting. Some angular momentum. And that's going to be measured in terms of radians per second, right? The angular frequency is radians per second. And so H bar is better used for momentum. So it's better used for physical momentum. And also it's often used for energy as well. Right? So we're going to see these two pop up. All right. And just remember, if you see H without a bar or with a bar, it just means a factor of 2 pi. This gives us a really, really nice equation. And this is what's called Planck's law. And this is perhaps the most important equation in this class, other than Schrodinger's equation, which I have introduced. Most important equation, which is called Planck's law. Named after Planck because he derived it with his constant. This is one of those that I would highly recommend just burying in the back of your head. Use. It's an equation I use on a daily basis in spectroscopy as a physical chemist. It's a super important law, and it's one of the easiest ones to remember. It says that the energy of a wave, a quantum mechanical wave of some frequency, is equal to H times the frequency of that wave. Right, so this nu right here, this is the frequency in hertz of a wave. Right, and this is the energy in joules. Super important equation, super easy to remember. You have a frequency, and even if you have a wavelength, we'll talk about that in a second. You have a wavelength, you can calculate it too. But anytime we want to think about frequency of light, we can always think about the energy contained in that light, and that's just that frequency times H. All right, so H in some ways is energy content of light or of any quantum mechanical system. Right? Anything that acts like a wave, an electromagnetic wave, something like an electron, or an atom, or like a light particle, photon, light beam, satisfies this equation. So you can, if you know the frequency of your light or the momentum of your particle, you can calculate its energy content. And that could be really important when you're doing spectroscopy. It's also important with chemistry. Right, so let's just think about that for a second. Right, so let's imagine you have a molecular. Right, let's just think about this for a second. You have a molecular sample. You got some molecules in here. So these are molecules inside of a small little petri dish or something like that. Right, imagine we're going to shine a laser at these things. We're going to irradiate them with some energy, light. All right, so we're going to choose a laser to irradiate these things. We'll just make it an orange laser. So I got this laser beam. And let's say, for instance, I have 1 mole of atoms. Right, now let's say we set up this experiment so that the beam is actually diverging, so that they all get irradiated with roughly the same amount of power. So what is the per photon? What is the energy content of a laser photon at, let's just pick a wavelength. Let's pick a frequency or a wavelength that would be common. We do photochemistry, we tend to do things. So let's do that. Let's set it to a classic example. We're going to do a wavelength of 193 nanometers. Right? This is a famous UV laser beam wavelength that's associated with a special kind of laser called an argon fluorine, or argon fluorine excimer laser. So it's a laser beam created by an electronically excited mixture of argon and fluorine gas. And this mixture generates 193 nanometer light. Set it up properly. Very complicated how it does that. It's a very complicated laser. It makes a very, very intense, very bright 193 nanometer light, argon and fluorine. So this is what we call a ARF plus laser. It uses fluorine cations. It removes electrons from the fluorine. They collide with the argon, and that collision causes laser. So what I want to know is how much energy does one of the photons impart on an atom if it absorbs it? Right, well, we can calculate that very easily. All right, so we're going to use Planck's law. Right, which says that E is equal to h nu. Right, but we have a wavelength here, not a frequency. So we need to convert between wavelength and frequency, which is perfectly reasonable. All we need to know is the speed at which the light is traveling, which is the speed of light. All right, so we can always convert frequency to wavelength by taking the speed of light divided by the wavelength. Okay, so this is equal to hc over lambda. The idea, the way we're interpreting this laser is we're saying per photon. And what that means is that this laser is shooting out little bullets, little individual bullets, one at a time. Okay, we haven't specified how many bullets it has per second. That's a function of the laser power. But you can imagine there's little bullets inside of here. Right, little light bullets. that are traveling in this direction. And the energy content of one is E equals h nu. Okay, so there are n of them. There could be maybe we'll think about like 1 mole of photons in a second. Okay? We'll do a molar energy. And then maybe on a homework we'll calculate how many. Eventually we'll calculate how many photons per second a laser emits. Then we can really think how much energy it really has. All right, so let's calculate. We have everything we need to know. We have two constants that are well known. We just need to convert our wavelength into meters. So this is 6.626 times 10 to the minus 34 little seconds. The speed of light is 299,792,458 meters per second. And we're going to divide that by our wavelength, which is 193 times 10 to the minus 9 meters. Right, a nanometer is a meter, 10 to the minus 9 meters, billions of them. All right, very simple calculation. I'm going to show you my magic calculator that I'm going to do this on. It's called Google. 6.626. As you can see, I've already done calculations like this recently. You can see my autocomplete. I'm going to divide it by, what was my 193? And just as a reminder, if you're confused what I'm doing here, I'm not using times 10 to the minus, right? E, just as a reminder, if you don't know this, this means 10 to the minus, so 10 to the plus. So E minus 34 is by definition 10 to the minus 34. Just the easy way to write it. 6.626 times 10 minus 34, 193 times 10 to the minus 9. All right, as you can see, it's a very, very small amount of energy. Right, it's about 1 times 10 to the minus 18 joules. All right, roughly. Right, that's a really, really small amount of energy. But the thing is that a laser outputs tons and tons of photons a second. Let's just say, for instance, it emits a mole, which is a very reasonable amount of energy, amount of moles per second. Imagine it emits a mole of photons per second, which is in fact a very reasonable amount. So let's think now the energy content per mole. Well, that's going to be 1 times 10 to the minus 18 joules times 6.02 times 10 to the 23rd per mole. Right, and that's just, well, that's easy math. That's 6.02, and we have a difference of 5, 10 to the 5. So 1 mole of photons imparts 60 kilojoules of mole of energy, UV photon. That's a lot of energy. Right? It's just under an electron volt. Right? It's not chemically a large amount of energy. For instance, bonds, right? Bond strengths tend to be on the order of about 400 kilojoules per mole. Right, let's just kind of roughly look at that, right? Bond strengths, typical bond strengths. So here's just an example from LibreText of typical bond energy. Right, bond energies for HH is 436, carbon chlorine is 330, single bond is 345. We're not imparting exactly enough energy just to cleave a bond homolytically with 2 radicals. Just scissor that bond. Yeah, but there's still enough energy to do something. And in fact, typically, when you put this into your molecules, especially certain types, and the molecules in particular that are really, really strongly absorptive in this region are double bonded. aromatic species, things that are conjugated, nitriles, things that have multiple double bonds, they tend to absorb strongly in this region. And what happens is that they absorb this photon. They absorb a large, like each one of them absorb maybe one, maybe two, but in general, each photon is giving 60 kilojoules per mole of energy. 60 kilojoules per mole equivalent of energy. What happens is that molecule gets excited into some excited state. Somewhere up there, excited state. What happens in the excited state is that the bond strengths change. All right. So when you're in a ground state versus an excited state of a molecule, the bond strength and the electronic structure of the molecule are different. Sometimes the atoms move, sometimes the bonds weaken. It really depends. And what happens is you pump it up into this excited state, and this excited state is floppy enough, it's got enough energy, and the bonds are floppy enough that it just falls apart. Right? When we do the iodine lab in the third rotation, you're going to see that happen. You're going to watch the light sweep over iodine's absorption, invisible, and you're going to see all these transitions that indicate that you're exciting the molecule to some excited state, and then it's relaxing. And eventually you're going to hit an energy where you've pumped so much energy into the molecule, the hydrogen bond just falls apart within two atoms. You can see that in the spectrum, that cutoff, exactly where you go from taking iodine into iodine and taking iodine into two atoms of iodine. And then that's because you're pumping a chemical amount of energy into the system with a laser. This is the power of laser spectroscopy and lasers in general, is that when you have this tightly focused, very, very bright beam of light, you can focus in on a very specific small object or small target, like a small sample of molecules. You can impart significant amount of energy that you could not do otherwise. And let me explain what I mean by that. If I wanted to imagine, I wanted to instead get 60 kilojoules per mole of energy from heat. And I want to put it in my sample into an oven and put it in a scenario in a situation where thermally it has an equivalent amount of energy versus a laser, right? Maybe a laser is too expensive. Maybe I can get the same thing from an oven. And so if we look at what the question is what temperature would you need to achieve this, to get 60 kilojoules per mole of thermal energy? You would need to set your heater to at least 7,000 Kelvin. Right? It's the only place that you would be able to achieve this is on the surface of the sun. Right? Because at this point, you're already melting steel. Right? So if you have some sort of titanium kiln, some sort of high melting, that's a tungsten would be a good example. Tungsten is very low, high melting metal. You make what do you call it? Like a reactor kiln that you put your molecules in, made out of tungsten or tungsten carbide, some material that melts at very high temperatures. You can heat it up really high. Even tungsten carbide is molten at 72. It's impossible, as far as I know, to get anything that hot, thermal, because everything falls apart. You can't make a reactor that survives that hot. But if you shine a laser in your molecule, you can get that equivalent amount of energy into the molecule, even at 1 Kelvin. You can have a molecule that's completely frozen in place, that's no energy whatsoever, a sample that's at basically 4 Kelvin, right below even lower than that. You can get it to below a Kelvin. You can create molecular samples that are below a Kelvin. And still, if you shine a laser at them, they will react as if you just put them into 7,000 degree furnace. Laser energy is extremely efficient. Extremely efficient. Right? This is the most effective way to generate energy and impart it into a molecule is through light, through Planck's constant, through Planck's law. There's always this momentum, this energy content in light, and it's much more effective than heat. Much more effective. Any questions about that? Okay, so that's a conversation about H. Right, we're going to see H all the time. It's just a number. I just want to give you some context to what it means. Let's go back to our problem at hand. So we have this free particle. Right? It's got this continuous energy spectrum. Right? It can be any energy you want. K can be any value you need. Right? We're going to make a change to this experiment. what I want to do now is I want to put my particle in a space, but I want to give it walls instead. We're going to put some walls. Right? We're going to see if anything changes. Does it still propagate like a wave? Does it have a continuous energy spectrum? We're just going to place some walls in our system. All right, this will lead us to something called the particle in the box theory or model. Now, if you guys have talked to people in the past that have taken this class, they probably will tell you I'm really in the particle in the box. And there's good reason we can learn a lot about the nature of the world just by looking at this very simple model. It teaches us a lot about chemistry and physics. It also, PIT stands for pain in the butt. You may feel that way too. We'll see. The idea is very simple. I'm going to take my free particle, I'm going to put it in this infinite space, and then I'm going to stick two walls at some finite distance that they can't escape. Right? I'm going to cage it, right, into an inescapable cage. So the way I'm going to construct this problem is, again, I have an infinite space, but at 2 points in this infinite space, I'm going to put two walls that are infinitely high. Right, I'm going to place one of the walls, I'm going to draw them in green. Like this. I'm going to put it at x equals 0. All right, so my left wall is at x equals 0. Again, I can choose anything I want, because it makes it easier. And then I'm going to put my next wall at length L. And there's another one at x equals L, which means that the length of this box, of course, is length L. These walls are infinitely high. Now, this is a one-dimensional space. What do I mean by infinitely high? What it basically means is that it hits the wall. The only thing you can do is reflect. All right, so these are 100% reflective walls. They're infinitely high. Which basically means 100% reflectivity. All right, you can think of them as perfect mirrors. It's not worth to think about mirrors because it could be a physical particle, but remember they're waves, right? So maybe a mirror is a good idea. Right? So what it means is they can't be absorbed by the walls and they can't escape the walls. Right? So they can only be confined within this box. So what I could do is just kind of casually draw some lines here to indicate that, again, it's completely inescapable. Okay, so inside of this box, I'm going to place my electron. We're going to go through the same process that we did with the free particle. We're going to write down an energy operator for it and solve for the wave functions that satisfy that energy. Now, if you think about this problem, it's really not that much different than the infinite particle, the free particle, right? The only difference is that there are regions of space where it can't exist, the regions where it can. Inside the region it can, it's totally free, right? This particle is allowed to do whatever it wants as long as it's not allowed to be labeled as jail cell. So inside of here, it's a free particle. And then outside it can't be, right? It's just basically just walled off, walled garden. Right, so let's go ahead and write our energy operator for this system. Well, we know that the kinetic energy of this particle is just a free particle, right? So we can just write it as minus h bar squared over 2m v squared dx. Okay, nothing's changed. In fact, we're going to see this kinetic energy operator everywhere we do everything. Because particles always move 1/2 mv squared. And that's what this is. All right. But we need to consider the fact that if we go ahead and plug in psi and calculate the wave functions that satisfy this operator, and satisfy the equation that we need, it's going to give us the same result as the free particle. If it changes. So we need to account for the fact that there's a space here that has a preference one way or the other. Right? I can specify each of my X points and say, is the particle allowed here or not? Right? So the difference now is that I have some bias about my space. Right? So the new feature is that each point in space is assigned what we call a potential energy. And that's all potential energy is. Potential energy is I have a particle or something that's moving with kinetic energy, and there are going to be a potential is some function that tells you whether that particle is preferred to be in a certain region or not. Right? So potential energy assigns an energy value to every point in space. Right? And so what that means is that if you're in a region where the potential is small, the particle doesn't have to pay that energetic cost to be at that position. You can imagine the potential energy of a single point is the cost of the ticket to be present at that point. Right? And so if there's a region where it's very energetically costly to be, ticket price is very high for that particle to be there, and therefore potential energy is low. So potential energy is a function of the space the particle is in. Right? So potential energy is a function of the space itself. It defines the box. Right? If we have some regions that it doesn't want to be, we should assign a very high potential energy for those regions. For areas where the electron's allowed to be, we'll assign very low potential, or none at all. All right, so what is the potential energy of this box? It's very, very simple. It's the simplest potential energy function we can come up with. Right, so for potential energy, we always write it as V. And this potential has two values. Right? If it's inside the box, it's a free particle, which means that there's no potential at all. It does not matter. Every single point in the box is exactly the same. Right? So we can just say that the potential is 0 in the region of the box. So that would be between 0, x, and L. Right? So it's in the box, the potential is 0. And then we want to create the box so that it's inescapable. Right? So we want to give it an infinitesimally large or an infinitely large penalty to be outside the box, right? So let's just set the rest of the potential to be infinity. So it's infinity if the absolute value of x. Oh, sorry, let me not write that. That's bad. That's not how this works. So it's either it's infinity if x is greater than or equal to L, or x is less than or equal to 0. So perfectly, there's no penalty to be in the box. There's an infinite penalty to be out of the box. Okay, so now we have the wave function now of our system, if you will, has two cases. Right? It's got the system that has some sort of evolution and some sort of behavior inside the box because the potential is 0, and it has an entirely different behavior outside the box where the potential is infinite. So we're gonna have to break this problem into two pieces. Right? We're gonna take it outside the box and inside the box. And then we have to try to connect those two answers together. Right? To have a function that's continuous over the entire space, satisfies all the properties that the system needs to satisfy. We'll go through those today. All right, so let's just set it up. So we have, let's just start with outside the box. All right, that's the easiest one. The potential here is infinite, which isn't really a number or anything like that. It's just infinitely large. And there's only one wave function that satisfies it. The trivial one, psi of x is equal to 0, right? Because what's the probability of finding the particle either outside L or x less than 0, outside the box? Well, that's 0, right? And that's going to be easy. That's going to be equal to the integral, as we'll see. We got this, or yeah, we did this already. From L to infinity of psi dagger psi dx, which is equal to the integral from negative infinity to 0 psi dagger psi dx. Right, these are all equal to 0. There's no probability. So the only function that satisfies all of this is psi of x is equal to 0. All right, well, that's really easy. What this means, there's no particle there. Right? There's no probability to see the particle outside the box. And the wave function outside the box is 0. Right out here. The only function that integrates to 0 is here. That satisfies all the properties. Okay, so there's no wave function outside the box. It only exists inside the box. However, we have a special condition now that we did not have before. The consequence of this is that this gives us a boundary condition for inside the box. So here's my space, X. Here's my box, L. Here's L in 0. Okay, and I'm going to draw the wave function in orange here, right? The wave function outside of the box and at the walls is 0. Okay, so what that means is that psi of L, which is at the wall itself, is 0, and psi of 0 is 0. Okay, so what that means is that whatever wave function we have inside the box has to go to 0 at the walls. That should make sense, right? Because if it's in the box and the walls are infinitely high, if psi of 0 is not 0, that means there's a probability to find it standing on the wall, right? Perched on the wall like a bird. But that wall is infinitely high. Well, it can't. So what that means is that whatever function's in here, it has to go to 0 here and has to go to 0 here. All right, so we don't know what that function is yet. But we know that whatever the wave function is inside the box, it has to come to 0. Right? Which means it could either come from the bottom, negative value, or from positive. Right? So it either has to come this way, or this way, or this way. Okay, so it either has to come in. But we know that it has to be 0 at each point. Right? This is now what we call boundary condition. Right? Our wave function has to satisfy that its values at the edges are 0. Right? We couldn't do that with a free particle, because a free particle just extends for infinity. Right? There is no boundary condition for a free particle. What that means is that our free particle solution may not work. Right? We're going to have to massage it so that the only allowed solutions of the wave function inside the box are ones that are 0 at. You can imagine we can draw a bunch of different, remember that the free particle wave function is a sine wave. Think of a sine wave at any frequency, right? We can choose tons of different frequencies or wavelengths for our wave that don't cross the 0 point at the walls. Right? So there's going to be frequencies of our wave that just don't work, because they don't go to 0 at the bounds, at the edges. But there's going to be certain frequencies that where the period of the wave, or half period of the wave, begins at 0 and ends at L. So there's going to be certain frequencies, say waves that fit perfectly into this box. Then there will be waves that don't fit. We have to choose the waves that do fit into the box. All right, so let's tackle the inside of the box. Inside the box, the potential is 0. Which means that the free part, right, the only thing that matters is the kinetic energy. Right, so we have, therefore, the equation that we need to solve, and this is all that we have is kinetic energy. Equation we need to solve is exactly the same as we had for the free particle. That whatever the wave functions that satisfy this problem, the second derivative of it gives you a number, the energy, times the wave function back. Right? Well, this is the same as the free particle, right? It's exactly the same equation we solved for the free particle. So we could write down e to the ikx. But the problem is that I just explained, not every e to the ikx satisfies the boundary condition. Right? For instance, I could easily, let me just copy this so I don't overwrite it. So the solutions here are the same. So they look like psi equal to e to the plus or minus ikx, but not all k's work. Let me show you what I mean by that. Right, so let me just draw the box one more time. And let's just do a graphic, right? Let's just think kind of roughly about what kind of functions fit in the box. Right, so we know that the function needs to be here at 0 and ends at L. Okay? So let's think of some waves that may fit, right? Here's one. Right, this is a half period of a sine wave. That works, right? That would totally be okay. Right? The integral of this is finite, right? Because it's finite length. Integral is finite. It's smooth. This is a half period of a sine wave. So we can calculate a frequency for it. Kind of think of it if the box is 2L, this goes negative and comes back up. There's the first half of the period, half wavelength. Everything seems to work here. It's a sine. This is a sine wave, right? This is a sine wave. This is some sine wave. Right, so that's perfectly okay. Right? We could also draw it like this. Right? That's a wave of twice the frequency as before. This would be sine of 2kx. Right? What's another one we can draw? Again, you can start to see the pattern we're doing here. You can have a period every half period. Like this. This is sine of 4kx. Right? And you can see I could just keep drawing waves. Right? I could just keep adding more and more periods, faster and faster frequencies, and I'm going to find a series of waves that fit perfectly fine. But imagine if I jiggle k a little bit. Right? If I start with this one and I jiggle k, I make it just a little bit faster. Right? What would happen? If I just add a little bit extra k, I'll do it in olive. Right? This is going to raise slightly faster, but it's going to fall down, and it's going to cross 0 at some earlier point. Right? And this is just going to continue, right? It's going to continue down like a sine wave. Right, like that. And so it hits the wall at some non-zero value. Right, so that wave can't work. Right, because it doesn't satisfy the boundary conditions. Right, so the only waves, the only free particle waves that work for our box are the ones that either are half period or whole period within the box. That the box is some fundamental, say the wavelength is the length of the box is a multiple of the wavelength. Or a fractional of half the wavelength. Right? And so what we can do now is just say, okay, well, sine seems to work, and we can argue it's not too hard to calculate, but you can get cosine to work here too. Right? But let's just stick with sines. Right? It says that the solutions for this psi of x look like a sine wave of kx for special k's, like the serial. Right? They got to be full of fiber and vitamin B12. Calcium as well. Right? So we need to figure out what those k's are. Right? We need to be the k's that, and obviously they're related to the length. They're related to the length because it means that length needs to be some multiple of the period or the wavelength. Right? So just think, we're going to think about it a little bit, and I'm not going to spend too much time deriving it, but the idea is that the solution is that k times L needs to be a multiple of pi for n equals 1, 2, 3, 4, and so on. Okay, so k is related, the values of the allowed values of k in our box are related to some number n and the length. All right, let's just convince ourselves of that. All right, so my claim is that the wave functions for this system, which I'll label n, which are a function of x, is some number a, which we haven't determined yet, sine n pi over L times x. Let's just make sure this works. All right, and remember, n is now, the important thing here is n is a positive integer. It has to be 1, 2, 3, 4, and so on and so forth, and nothing else. I should maybe say the absolute value, but let's just keep it to positives. Nothing else. All right, so now we have a limitation. Our k now, kx, is now a function of an integer. K can't be any number at once, but k is n pi over L. K has to be an integer multiple of pi over L. Right, so in the box, the only allowed k's are where k is equal to n pi over L. All right, we have a limitation now. We can't take any value we want, meaning that if we have a box of length L, and imagine we were like throwing particles into it with some momentum, like LeBron James, so like little alley-oops into this box. All right, and what this is saying is that only specific trajectories or momenta that LeBron shoots his little particles into the box will be trapped in there. So if he throws it in where his momentum is some multiple factor pi over L, then they get trapped in that box and they reflect back and forth forever. Imagine you can like throw it into the top, right? Then it doesn't escape. But if he throws it in with a slightly different value, it's not exactly n pi over L, that particle does not get trapped in a box. It disappears or it escapes the box. It doesn't reflect forever. It's not a stable state. So only the stable trajectories inside the box are the ones that have this momentum that is some factor, some integer factor of the length. Right? That limits things. Because let's just look at, now let's compare our energy spectrum, right? What is the energy of this system? Right, so let's calculate the energy now. So we're just going to apply T on psi n. That will give us the kinetic energy by measuring it. That's minus h bar squared over 2m times the second derivative of our wave function, respect to position. This is minus h bar squared over 2m. The first derivative of my function gives me a cosine. From the chain rule, I get a factor of n pi over L on the outside. and it's a cosine. The first derivative is a cosine n pi x over L times n pi x, or n pi over L, right here. So now I'm going to take the derivative again, because it's the second derivative. Second derivative of cosine is negative sine. And I get an additional factor of n pi over L again from the second derivative. So this gets squared. And because cosine goes to negative sign, I get an additional negative sign out. This one goes away. And I'm left with my original function. I'll write in orange here. Okay, and just simplifying, this is h squared, h bar squared, n squared, pi squared over 2ml squared times my original function. Right? Remember that this equation gives me the energy back times the original function. Right, so this is my energy. This is the kinetic energy of my particle in the box. This is my energy. Enjoy your haircut. Yeah, you're welcome. So, all right. Well, we now have an interesting function for our energy. That's a function of n, which is a number, an integer, some pi's and then the length. Right, so now the energy is dependent on the length of the box. Right. Let's simplify this a bit, because remember, let's use our fact that h bar is 2 pi h. Right. We've got some pi's in here. Let's see if we can cancel some stuff out. All right, let's just try to simplify this equation. All right, so we have the energy equal to h bar squared n squared pi squared over 2ml squared. And we're going to use the fact that h bar is h over 2 pi squared, n squared pi squared over 2ml squared. All right, you can see there's some cancellations here. And so I can get rid of the pi's. I have a factor of 4 in the denominator now. So I'm just going to write this in big text. Now we have an energy that's dependent on this value n, which is h squared n squared over 8m, where that's the mass, L squared. And remember, n now takes an integer. It can't be any value, right? It's not like k for the free particle, which can be any momentum you choose. N can only be a positive integer. So what's the consequence of this? Well, we don't have a continuous energy spectrum. Particle in the box only takes specific values of the energy. It takes one factor of h squared over 8ml, that's where n is 1, or 4 factors of it, or 9 factors of it, 9 times this number, or whatever, 5 or 25, or 16 and 25, or 36, right, which is all the squares, the perfect squares. And so there is no particle in our box that has energy, say, 3 times h squared over 8ml squared, because there's no integer n squared that equals 3. So there's gaps now in our spectrum. Instead of having a continuous energy spectrum like a normal particle, a normal billiard ball, we now have gaps. There are only certain allowed energies, and they're quantized. What we call quantization. Right? They're quantized because they can be referenced to the first energy level, the second one, the third one, the fourth one, the fifth one, the sixth one, and there's nothing else in between. They're countable. They weren't countable before. We couldn't count a continuous set of energies because there are numbers that you can't count, right? You can't count irrational numbers. They're uncountable numbers. So we can't label them. There's just an infinite amount of them. They're indexed by some number that varies. And here we have a countably infinite amount, right? I can always go, this is the first one, this is the second one, this is the 10 millionth, this is the 100 billionth energy level. Maybe infinite. But I can always count them, which means if you can count them, That must be there must be gaps. Must be regions of the energies that have no levels, meaning that there are energies that don't exist for this part. So let's look at what this looks like, just kind of finishing up graphically. And so for our free particle, I've already drawn this, but we'll just do it again. I'm going to plot the energy of our system as a function of K for our free particle. Remember, K is this number that we use to define how much momentum we have. So EK, the h bar squared, K squared, over 2m. Right? And so the lowest possible value for K is 0. Right? And of course, the energy of that is 0. Right? So in the free particle, there's a state we can create a particle that isn't moving, has no energy and isn't moving. It's so stationary, floating in space with an absence of any kinetic energy. Totally allowed. Right? And there's a continuity, continuous spectrum of possible energies that go as K squared. Right? So I can just keep pushing, I can keep kicking my particle more and more and more initially, and it goes faster and faster and faster. And this scales as K squared. Right? So there's like K equals 1, K equals 1.5, 2, E, pi, 42, and so on and so forth. Right? I can take any value I want, and I get an energy out. Right? But in the particle in the box, don't have that luxury. Now I have this new number n, which can only be an integer, positive integer. Sorry, h squared. 8ml squared. And so here on n, instead of k, I write n. That's how we index our energies, n. And I can only write 1, 2, 3, 4, and so on. And these energies are going to be at specific values. Okay. E equals 1 is that h squared over 8ml squared. 2 is going to be at 4 times this. Right, and so on and so forth. The next one's going to be up here. Right, and we could theoretically, right, so we could theoretically draw, not the best in the world, let me just fix that. We could theoretically draw a parabola that connects all these points. These are our first three energy levels. But there's no energies between them, right? These are completely imaginary. There's nothing here. There's no energies in between these values. So if I have a particle of random energy in my box and I'm asking you what's the energy, I know for a fact, right? Let's imagine I have a random particle. I don't know what the energy is. Measure it. I know for a fact it's going to be here, 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 4, 5, 6. It could be any of these, and it's not going to be anywhere in these regions. Can't be, by definition. So we have the same kind of energy structure, right? These are increasing as that number goes squared, right? So it kind of still looks like a particle, free particle. It still goes as k squared, but there are now gaps in the spectrum. This is a gap. And this is a gap. And this is a gap. So on and so forth. So what we say is that the spectrum here is discrete, right? That's the opposite of continuous, right? Which means it has not continuous. And it's quantized, which means that it's indexed, the values are indexed which are in this case energies or measurements, are indexed by a countable number or an integer. All right, we can say that this has, right, what can we say about the particle in box? It has 1 unit of energy, it has 2 units of energy, it might have 3 units of energy, but it can't have 2.5, it can't have 3.14. It can only have quantized units of energy, little packets of energy h squared over 8ml squared, because we only allow values. All right, so we call this a discrete spectrum. It's not continuous, there's gaps, and it's quantized, meaning that each value has an index number associated with it. We can count them. It's countable. And it's very, very deep mathematical and physical consequences. And this is entirely general. I'm just going to write this down. Any particle trapped in a attractive potential, right? Not a potential where it wants to kick it out, but a potential where it's safe to be in and it's stable, will have a discrete and quantized spectrum, quantized set of energies. We'll see. We'll come up with different boxes to put things in. We'll take an electron and put it in a attractive potential with the proton. We'll put it in we'll build a spring. It has a spring-like potential, which is attractive. We have a particle in a very boring box. Every single time we're going to realize that the energies have gaps and that we can always count. It's infinite, probably, but we can always count and label our energy levels with a number. Completely universal. Right? So this is our first instance of this quantization. So what we're going to do next class is to come back to this, look at this, and see what else we can learn about this. Right? What other properties do we get that are strange? Because we already have something that's very non-typical for the energy. It's got gaps. But what happens to, say, the position that we measure, or the momentum, or different properties of the system? Right? So we'll look at that next time. And then we'll try to apply this to a chemistry problem, and we'll find that it works amazingly well. All right, have a good one, guys. Thank you.